This is an example of finding the magnetic field when we have a situation with a magnetic material and we have a symmetric situation. In this case, what I'm going to say is I have a torus of iron. Okay, that's this gray torus here. It has a small gap there, and I wrap this torus of iron with a wire that carries a current I. I'm going to say that I have 100 wrappings, that the current will be 1 amp, because here the overall question is I want to find the magnetic field in this torus. Specifically, I want to find the magnetic field in the gap, and so that's what we're going to be doing here this time. So ideally this, let's see, so looking at my right hand rule, since the current is looped around going up through the center of the torus, that's this way, my magnetic field is going to point along this direction. Okay, so it's going to point that direction through the gap. So how do we go about doing this? Well, to go about doing this, what we want to use is we want to use the Maxwell's equation for magnetic material, which is del cross H is equal to the free current. So the way we're going to solve this problem is we are going to use the equation for magnetic material, or the equation to find the H field whenever we have a magnetic material. That equation is such that the curl of the H field is given simply as the free current. Really, we're going to use the integrated form of this. So the fundamental theorem, when applied to this, is going to give us the integral over a closed loop over the some surface dl dot H is going to give us the enclosed free current. Okay. Here I know the enclosed free current. Oh, I have to figure out what loop I'm going to draw first. So we're going to look at the loop. I'm going to draw this torus from the top. And so this torus is going to go around like that. We have our wrapping. Our wrapping comes in under the guy, goes over, 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 so under, under, over, under, over, under, over, 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 under, over, under, over. And it leaves like that. And so the surface that we're going to look at is, we're going to look at a circle drawn here, and the surface through here is the surface we're going to look at. So the circle is delta S, and the surface here is S. The current that flows through this surface, obviously, because we're only getting the current that comes up, we're not getting the current that goes back down, is going to be however many windings we have, which is 100 windings, and the current carried through each one of those. So on the right-hand side here, we're going to get N times I. On the left-hand side, we're going to make an assumption. We're going to make the assumption that because of the symmetry of this problem, that the magnetic field H, or the H field, I should say, not the magnetic field H, but the H field, which is a vector, is only going to be in the phi hat direction. I know it's going to be in the positive phi hat direction, which is in that direction, because of the right-hand rule. And it will only depend upon the radius out to that point, which is S. Okay? Phi hat. And so this is a simplification we're going to make. When we plug that in here, it doesn't depend on the angle, so we just have the circumference here multiplied by this h of phi hat. So this is 2 pi S times h phi S. And that's all, and that's it. And so now we've found the magnetic field H everywhere. So the magnetic field H of S is going to be, here's a little bit of fun, no, let's not worry about this. Magnetic field H of S is Ni over 2 pi S, and this is true as long as we're inside the torus. Okay, it's equal to 0 for outside the torus, but we're going to say this is true if we're inside the torus. True if inside the torus. Okay, but what about in this small gap? Well, to find the small gap, we have to get from this magnetic field H to the magnetic field B. And to do that, we're going to use the following constitutive relation, which is for a linear material, which we're assuming that we have a linear material. For a linear material, magnetic field B is going to be mu times the magnetic field H. Now, we don't actually have mu directly. We have this mu over mu naught, just slightly inconvenient, but that's easy. We just multiply and divide by mu naught. So mu over mu naught times mu naught times magnetic field H. And there we go. So now we are ready. We can write down B. So B, and this is again inside the torus, is going to be, in this case, mu naught, mu over mu naught, N I over 2 pi S. Well, that's pretty cool. Phi hat. Phi hat. And again, this is inside the torus. Now comes the trick. Now we're going to look at electromagnetic boundary conditions. E and M boundary conditions. Now I'm looking here in this gap, and I say this is a small gap, and that's important. So really the torus is going to go around here, and I have a very small gap compared to the size of the torus. Now if I look just at a little area such that it's slightly inside the torus on one side and slightly outside the torus on the other, I can write the electromagnetic boundary conditions in hat dot B above minus B below must equal 0. This was a consequence of the del dot B equals 0 Maxwell equation. And so this is what we call the electromagnetic boundary conditions. So that's that right there. Well, I know that B below, which is this area right in here, is going to be this B. And so the B above has to be the same as long as the surface is perpendicular to the statement that we want. And it is. So this was even true in the gap because of the electromagnetic boundary conditions. Because of the E and M boundary, E and M boundary conditions, this is true in the gap. We have the magnetic field in the gap is mu naught, mu over mu naught times N by I 2 pi S phi hat. Okay, in gap. We're not quite done because we gave some numbers, and it's actually interesting in this case to figure out how big this magnetic field is. So we should just go ahead and plug in some of those numbers. So we can see all the numbers now. If we want S, which is the radius, to be 10 centimeters, we're going to have that the magnetic field is going to be equal to mu naught. I know that mu naught is 4 pi times 10 to the negative 7. In the proper SI units, I'm going to leave units off. I'm going to work in everything in SI, which means I'll get Tesla at the end for magnetic field. Mu naught over mu is 5,000, which is a reasonable number for properly annealed iron. So if you have a pure enough sample of properly annealed iron, you can get a mu over mu naught of 5,000. N, we have 100, and for I, we have 1. On the bottom we have 2 pi, and for S we have 10 centimeters, which we're going to write that as 10 to the negative 1 in SI units, because meters are the proper SI units. And now we start looking at everything. First of all, the pi's cancel perfectly. We get a 2 down here. This 4 will go to 2, but then that 2 I'm going to put over here and make this 10,000 instead of 5,000. And so now we only have powers of 10, which is kind of nice. I have 10 to the negative 7, 10 to the positive 4, 10 to the positive 2, and 10 to the negative 1 on bottom. That's all perfectly cancels out. This says I have a field of 1 Tesla in the phi hat direction. This is actually really kind of interesting. I don't know if this is really possible. I have a feeling before you get to Tesla, you're going to get to what's called a saturation point for this magnetic materials. If you remember, these magnetic materials that had a very strong response, all these are ferromagnetic materials. Ferromagnetic materials have a pattern, if you remember, they have this hysteresis loop. And in the middle here, if you do a small applied magnetic field, you can get it to act linear, you can get it to act paramagnetic with a very, very high slope. And so you can get this very strong response. However, it's a little bit hard to believe that you can have this loop last all the way to 1 Tesla. I find it a little hard to believe that you'll get that to work all the way to 1 Tesla. You'll get such strong response. You would get to this saturation field up here, I think, well before you got to that Tesla. So doing the problem using a linear approach, which is what we did, we just assumed that we had a linear material. We find that we eventually get a field strength of 1 Tesla. I don't know if that's actually physically possible or not. It is kind of interesting. But anyways, now you know why iron core magnets are so much stronger than non-iron core magnets. This would be weaker by a factor of 5,000 if you didn't have an iron core here.